So the simulation is the basis for analysis of robot operations. It supports the programming, and it's quite an important part because using simulation we can zoom in and out in the system itself, but both in terms of geometrical properties, in time, and different kind of functionalities we can try out, how things works and so forth, different situations. And this also relates to the different levels of intelligence in the system for different applications, and the opportunity to optimize the performance of the robot for different kind of tasks. And then we also have support connection to the robot systems. Usually we talk about offline mode, which normally is simulation based, and online mode, which is direct connection to the robot. So, programming a robot. Describing the task for the robot. The task is the job the robot should do and may include controlling process, the moving of the robot arm for different workpieces in 3D space, or devices, whatever it is, interaction with workpieces, meaning interaction could be between the robot and effector to the workpiece, but also different kind of processing operations, which could be welding, laser cutting, polishing, deburring, whatever actually, and interaction with other robots, machines, operations in collaborative modes. So some basic definitions, which also are part of the standards terminology related to robotics. So a task program is a set of instructions for motion and auxiliary functions that define the specific intended task of the robot. And an application for an industrial robot could be arc welding, polishing, machine tending, assembly. That is general area of work. A task is a specific within the application, meaning the task could be to arc welding a specific work object or work objects to each other, but the application is the process, arc welding, machine tending, and so forth. Control program is the inherent set of control instructions which defines the capabilities, actions, and responses of a robot or robot systems. Definitions 2. A task program is the act of providing the task program. Manual data input programming is the program generation and entry directly into the robot control system by means of switches or plug boards or keyboards. And teach program online is programming performed by manual leading the end effector or manual leading a mechanical simulation device, or using a teach pendant to move the robot through the desired actions. I would say that teach pendant is the normal way to program robots using the online methodology. But for certain cases, there are manually leading the end effector, like for spray painting and so forth. And there are systems which incorporate the ability to do some fine-tuning or touch-up of orientations, poses, and so forth by dragging and leading the robot and touch up what is actually programmed beforehand. So that could be a combination of these kind of things. And offline programming is the programming methods where the task program is defined separate from the robot for later entry to the robot. This is usually where simulation systems come into place. And goal-directed programming is a programming method in which the task to be carried out is defined, but the path of the robot is not prescribed, meaning that it could be that different actions are defined by placing, for example, work pieces, objects, or defining that certain actions should be done, like grabbing something from a machine tool, but not the exact path. The path of the robot and effector has to be planned and calculated by the system that actually is used for programming the robot, which normally is a software piece plugged into a simulator. And then that can be checked so that we don't have any collisions and so forth. So, comparing online and offline programming, what are the differences? What are the pros and cons? So, a general definition is that offline is something not presently active or available for access within a system. And online is something active or available for access in a system, where a system is actually the robot system in this case. So online programming is a common method to program computer controlled production processes today, and that is the online method, so to say. An online method involves direct access to the real control system, and that all operations are carried out on the real system. The real system is actually both the control system and the robot and all the peripheral related and connected to the robot, with some limitations. Because if the processes to be carried out are somewhat, they could be restricted, like we do not operate like laser cutting, we do not operate grinding operations, or things that actually from a work environment point of view might cause some injuries to the operator. So still, I mean, some processes can be checked, others cannot be checked for normal or natural reasons. They have to be run remotely and checked by other means. So we have access to the real robot, and equipment is required, and usually the robot is programmed using some kind of a teach box or teach pendant. Teach pendant means some buttons to actually activate and define instructions, and some kind of, normally joystick, could be also buttons to actually move the robot around in the workspace. And that also, of course, include emergency stop buttons and so forth. So traditional online programming means the direct interaction with the robot. We use the same hardware during production as during production, which means robot, tools, workpieces, and so on. And the robot is moved from pose to define motions together with controller arguments, which might be, for example, velocity, how the motion is to be carried out, I mean, which interpolation mode and so forth, which configuration to use by the robot. I will go through that later on. And we have an interaction with handheld terminal, often with an integrated joystick. And yeah, it could be like this. And it really depends on the application. I mean, what type of auxiliary equipment is connected to the robot to actually perform what is to be going on in the cell. And sometimes not everything can actually be verified during online programming, which has to be during a run-in phase where everything is tested in the real case. Offline programming takes place on a separate computer with dedicated system, software, and the robot programs, they usually verify with syntax check and or a simulation. and the robot program is normally downloaded to the robot. In some cases, there could be a direct connection, so they are checked side by side, so to say, simultaneously. So there is some kind of specialized editor, which is vendor specific, with syntax checking and so on, and also a graphical system, a graphical view, which show the system as it would run using the program written in the specialized editor at the same time. So offline models in car systems usually includes the robot, and these kind of systems usually have a large set of different robots available. If they are not available, they usually offer the ability to model new robots on the fly, so to say. We have control systems, which could be the true control system of the target system or a emulation of a robot system. We have different kind of tools and effectors. We have external axes if needed. We have some peripheral equipment and environment around. Could be fences, could be whatever. We have some kind of teach pennant or editor to actually generate and add instructions which are similar or the same as the target system instructions. And we have a process or an application we work with. And if the process within the application require that, there is a controller for that as well, which we have to take into account. So for offline programming, and that is also for online actually, but it's more evident for offline programming, there is no standard in existence for robot languages, for different kind of robots from different vendors. So a translation is normally necessary if the robot system that we use for programming and simulating the system is different from the target system vendor. And we also need, of course, 3D models of all objects. Otherwise, we will not be able to do some kind of simulation. So we create the robot program structure. We develop a world model to create the robot system with all its peripherals. We have some know-how, often related to the application and the task program. And then we generate the task program for the specific case we are actually working on. Then, when everything works, we can translate to the target system, download to the robot controller, check that things actually work. So, some pros and cons, and actually, what are the differences? Offline programming, robot is productive during programming. A 1 minute robot cycle can result in hours more of programming. And I wouldn't say that offline programming is faster, but we don't occupy the system during the robot system during programming. We can work at the office in our own pace. We can design and program new robot systems in advance, meaning that we don't need to have the robot while we are modeling, trying out new kind of ways to perform the application and try out the best options, so to say. Usually we get a better quality and documentation of programs. We can reuse what we've done before in a better way. And of course, we can also try out different aspects related to safety without any injuries, because that is only in the virtual world, so to say. As for online, we have a less accuracy problem for defined processes as compared with offline programming. In principle, what you see is what you get, so to say. We have the real system, we do programming on the real system, and actually we drive the robot to whatever pose and target we are aiming at. So if it works, it works. The functionality is tested continuously during programming, but only for, I would say, simple programs. For more complex programs, it might be a huge complication to apply online programming, especially if we have more than one robot in the same work environment. We might have collisions that we have to take care about, and to try out the best way to avoid these kind of things might be very complicated. And the robot operator perform programming, and that person usually knows what is going on and has some kind of experience. But if complex tasks are complicated, I would say that simple tasks made simple, it's a good thing compared to offline programming, where even simple things might take a longer time than for online programming. So a combination is fruitful in many cases. So modules in offline simulation systems. Well, a geometrical description of the world model, as mentioned, in forms of CAD model. Possible to build and simulate hierarchical link mechanisms different ways. Link mechanisms might be others than robots. It could be different kinds of positioners, traction, servo tracks, could be complex end effector tools and so forth. We also, of course, can include kinematics and dynamics. We have collision detection. We have a translator to the language of the target system, and any kind of instructions that are specific for the target system. And of course, calibration support of the model. So what we mimic and emulate in the simulator should be the same as in the target system. So examples of how it could look. This is example from Robot Studio, kind of geometrical features and more in close-up view for an assembly task. There are some specifics related to robotics also that one have to consider. I will go through that later on. But we have an interrelation between different axes of the robot, like the primary and secondary axis and tool center point, meaning that to reach a specific area here, the robot might come to the same tool center point but uses different configurations. And this is quite often that one have to actually decide what type of configuration should be used to reach that, and then try to have the same configuration for the whole task program if possible, or at least for some part, so it doesn't mix up different configurations, because then it has to switch over and might come in collisions, and also run the servers, which takes time to come to the next type of configuration, usually by turning 180 degrees of some server drives. Also, could be something like this. So there are a number of different kind of configurations for most poses in the 3D world. And yeah. So one can think about how much should be modeled when we do some kind of modeling for simulation. What tolerance levels should be used, and what dynamic objects, meaning moving objects, cables, and so on. And how do we model and simulate sensors? In principle, I would say that you shouldn't model more than what is necessary. What is the purpose of the simulation? What is the purpose of the programming effort? In some cases, it could be that we only model things that are close to what the robot is moving around, meaning we have a work table, maybe we have end effector, we have the work objects, maybe a jig where the objects are placed within, and not much more. In other cases, we add fences, uh, vacuum tubes, or pressured air tubes for the end effector, more or less everything what is included, down to 5 mm or even smaller objects, just to avoid possible collisions because we move so close to these kind of things. So it really depends on the application and what we're aiming at. Moving objects might be tricky, but especially if we have things like assembly, we have a conveyor belt where things are coming into the system. We need to be able to feed the system with new objects. They should disappear after we have done some work and so forth. So it really depends. But that adds complexity to the assembly task. And how to model simulate sensors. If we have just a binary sensor, that could be pretty simple. If it's more complex, like a sensor, like a vision system or a triangular measurement system, we need some more complex models to be able to track down what is going to happen. In some cases, that is important. In other cases, we don't care about it. We just assume that everything is working fine and the sensor is driving the robot to the right place in time based on how it works. So it really depends. But if we model sensors, it might be quite complex. Okay, next we go to translator to the target systems.